Hi everyone, I'm Jamie. So, one of the many side effects of this pandemic is that a lot of you are probably doing a lot more math at home with your kids than you typically do. It is possible that you're revisiting your memories of math class and talking about math rules that you learned when you were a kid, which is totally normal, and I remember learning those rules too. And naturally, we default to what we know. However, here's the thing about math rules. Some of them are really just tricks that we call rules, and they get in the way of students mastering concepts. Also, many of those rules expire when kids learn more math content. So I'm going to go over some of those rules and tell you about when they expire and give you some ideas for what we can talk to kids about instead. One very common rule that young students learn is to look for keywords to solve word problems. Often, when students are first learning to solve word problems, they're told, hey, all you have to do is look for these specific keywords, and they'll tell you what kind of math you need to do, like total, all, together, left, etc. So there's a few issues with that. Firstly, it's teaching kids that they don't even need to make sense of the problem when we actually want them to do the opposite. We really do need to teach kids mathematical literacy, which means figuring out the problem in a context. For the most part in our lives, math happens in a context, and we want kids to experience that. The second problem with that is that it's not going to work very well. I'm going to show you a few example problems, one where a keyword search can work, and a few others where it doesn't. Okay, so when I look at this problem, Mohammed had 15 guests at his birthday party. 4 people went home early. How many people are left? If you were doing a keyword search, what a lot of people are going to do is they'll say, okay, I'm going to highlight my numbers, and then I'm going to highlight my keywords. So if I highlight these numbers, highlight 15, highlight 4, and highlight left. Now, a lot of people are going to be thinking, okay, so left means subtraction, which means that I'm just going to do 15 minus 4 equals. Okay, in this situation, that is accurate. However, the problem is that I haven't thought about this problem at all. I haven't thought about what any of the words mean. I haven't thought about what's happening. I haven't thought about whether or not this makes sense. I've really just turned off my brain, highlighted, and written an equation. That's not how that's not how people really do math in real life. So I'm going to show you another example where that would not be a very successful strategy. In this problem, Jane says there are 12 superheroes in the Marvel Cinematic Universe. John says there are 16. How many more superheroes does John think there are? All right, let's go for Old Faithful. We're going to highlight our numbers and highlight our keyword, which is more. Okay, so more means addition, right? Because that's what keywords are for. So 12 plus 16 is 28. Is that what this problem is really asking? It isn't. This is a comparison problem. John has one view of the Marvel Cinematic Universe, and Jane has a different one. So they disagree about how many superheroes exist in this universe. John thinks that there are more. How many more does he think? How many superheroes do they have to argue about? That's the real question. So in that case, if I stop and make sense of the problem and think about what's really happening, I need to do subtraction. 16 minus 12 equals 4. Let's look at one more to think about how we can get around this, this issue of just thoughtless math problems. When my family gets together for Thanksgiving, there are 19 people all together with both kids and adults. So if there are 10 adults, how many people will be sitting at the kids' table? Again, I can look at just these numbers. I can highlight my 19 and 10 and all together. Another great keyword that people think means addition. Okay, so I have 19 people all together, kids and adults. I'm going to put 19 plus 10 equals 29. Is that what I am asking? It's not. If I know that I have 19 people total, 10 of them are adults, and I want to know how many are sitting at the kids' table, what do I really need to do? I really need to do subtraction. So if you're wondering, oh my gosh, but my kids really struggle with word problems, I don't know what to do, how can I solve this problem? We want kids to be drawing pictures about what's happening. So there's a couple ways they can do that. They can draw an actual picture of what's happening, which is what kindergartners and beginning first graders might tend to do. And when they get a little bit more efficient at that, they will start to just draw representational pictures. So a kindergartner might actually draw 19 people. A first grader might start to just be putting X's to represent the people, and a second grader will probably just be doing like circles or X's or something. So if I were going to show second graders how to do it, or if I were sort of showing the second grade class what other second graders were doing, I would say, okay, there's 19 people all together, right? So let's put our people down here. Let me make this smaller so that we have space. So I'm going to draw my people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, I have drawn 19 X's to represent my 19 people. And now I'm just going to color code this. Here are all of my adults. That means that these are my kids. And I didn't even have to actually write an equation here. Because I've drawn it, I've made sense of the problem, and I can just see that this is there are 9 kids. So that's how we can get around that issue. This rule comes up a lot, particularly with young students. They think that the equal sign means find the answer. So there's 2 reasons for that. One reason is that humans notice patterns. It's what we do. We are so good at noticing patterns that we see patterns when they aren't even there, which is why we can find animal shapes in clouds in the sky. So when kids think that the equal sign means solve, it really makes a lot of sense because in most of the problems that they've seen in kindergarten and first grade, that is effectively what it means. So in that respect, the students are being great mathematicians and they're making generalizations about what they've seen. The other reason that kids tend to think that equals means solve is because sometimes adults tell them that. That is on us, and we need to stop that. Equals doesn't mean solve. It means that there is a relationship of equality between the things that are on one side of the equal sign and the things that are on the other side of the equal sign. This is definitely something that the kids are going to need to understand in algebra when they're moving things around from one side of the equal sign to the other, but they also need to get this concept in early elementary school as well. When kids are learning about decomposing numbers into their parts, they work on the idea of, say, like 8 is the same as 3 plus 5. It's also the same as 1 plus 7. So we want students to understand that numbers can be decomposed in different ways, so they need to get 3 plus 5 equals 1 plus 7. And the equal sign is showing a relationship between those 2 things. When students are working with larger numbers and they're crossing tens and hundreds, we want them to understand that 9 plus 2 is the same as 10 plus 1, or 99 plus 3 is the same as 100 plus 2. It gives them a greater flexibility with numbers. A group of elementary school students were given this question, and the results are disappointing, but not terribly surprising. Out of the first and second grade students, only 18% of them knew that the answer was 7. And in grades 3 and 4, about a quarter of the students got the answer right, and in the upper elementary school, it's better, but it's still less than half. So on the one hand, this means that students don't know what equals means. On the other hand, as I said, it means that they are definitely using their skills of generalizing and pattern recognition, which is a good thing because those are great mathematical skills. So glass half full, half empty. So the thing is, though, that we adults need to do several things. Firstly, as I've already mentioned, we can't tell kids that equals means solve or just do something. That's not accurate. And secondly, we need to vary how we write problems. We can write 8 plus 4 equals whatever, like this is a very traditional method. We also need to show problems that look like this. Something equals 8 plus 4. And then we also need to show problems that look like this. 5 plus something equals 8 plus 4. This is going to give students more exposure to this idea that these two quantities, the total quantity on either side of the equal sign, need to be balanced. The rule that longer numbers are larger is something that students start to think about in lower grades, kindergarten, first, maybe second grade. This is especially true when they're learning about place value. They're comparing numbers and they're putting them in order from smallest to largest or largest to smallest. So kids are often told, hey, you just have to see how many digits are in the number, and then the number with the most digits is the larger number. But that is not true. And it becomes really clear that it's not true when students get to fourth grade and they start working with decimals. So let me show you what I mean. In this case, we have 1, 2, 3, 4 versus 1, 2, 3, 1,234 versus 123. All right, so 1,234 is larger than 123 when kids are first learning about place value. They're thinking about the greatest number of digits will be consistent with reality. However, if you were to add a decimal to this and it was 12.34 versus 123, now the situation has changed and this number is smaller. So we want students to be thinking about the actual value of a number, not just blindly following a rule that doesn't encourage thinking and it isn't even going to work for very long. Here's another example. We have 0.8 versus 0.75. So students will often look at this and they'll think, well, 75 is 2 digits. 0.75 is 2 digits, 0.8 is only 1 digit, so 0.75 is bigger than 0.8. So we know that that's not correct, of course. So there's a few ways that we can handle this issue with students. The first way, of course, is not to tell students this rule and don't try to give them a shortcut that isn't really very helpful and isn't truly a shortcut. That does not mean that students aren't going to get to this idea on their own. As I said before, people tend to notice patterns and they might just go ahead and get this misconception based off of their own ideas from earlier grades. And they might not even need an adult to tell them that before they start to think, ooh, I've got an idea. So if that happens, we can always build the numbers. Either with manipulatives or drawings. Being able to see what the number looks like always really helps to clarify what we're talking about. The second thing to do is to name the numbers accurately. When I was speaking about these numbers previously, I called them 0.8 and 0.75. That's not what those numbers really are. By calling it 0.8 and 0.75, I've taken away the value of those numbers. It's really 8/10ths and 75/100ths. And when students are beginning to learn about decimals and tenths and hundredths, they will learn that 1/10 is the same as 10/100ths. So 8/10ths is the same as 80/100ths. If we call numbers what they really are, it will be a lot easier for students to just recognize right away that 80/100ths is a greater value than 75/100ths. All right, friends, that's all the ideas I have for you today. There's plenty more rules for us to talk about another time. So I hope everyone has a great day and everybody stay safe. Ciao.